Hello everyone, welcome back. Today we will be talking about class variables and functions. We are going to build on something that we already know about, which is classes and objects. Up to this point, most of our focus has been on data and functions that belongs to individual objects. Every object has its own state and each object behaves independently. But we are going to look at situations where that might not be enough for us, where we might need to share something across all the independent objects of a class that we are talking about, instead of each object keeping a private copy of its own. So, before we introduce anything new, let's spend a minute refreshing on an important idea, which is a class is a blueprint. It describes what an object would contain and what it should be able to do. By itself, a class doesn't store any data in memory. But an object is an actual instance of that class. When we create an object, memory is allocated for its member variables. I like the comparison where the classes are actually compared with data type and the objects are compared with variables, as you can see on the slide. Also, you can see there's an app screen illustration here. We have one class called app screen, but we can create many different objects from it. A new screen, a setting screen, a profile screen, all follow the same blueprint, but each stores different data. So one class can produce as many independent objects as we need. Notice that the app screen stays the same, but the data within it updates according to how we prefer it. Now, let's think about a practical problem. Imagine we are building software for a university. We have many students. Some belong to software engineering, others belong to electrical or mechanical. And suppose someone asks a simple question. How many students are there in the university? As simple as that. So it sounds easy, but think about where that number should actually live. Every student object represents one student, but the total number of students isn't really information about one particular student. It's information about all students combined together. As new students are admitted, the number should increase. When students graduate, it should decrease. So here's the question I'd like to keep you in mind. Where should we store that counter so every student can contribute to it and everyone sees the same value? Where should we put it? We will explore a few possibilities before we look at the solution. Let's think through some possible designs. One idea is to make the counter a normal member variable inside the student class. Okay? At first, that might sound reasonable, but remember what happens with member variables. Every object gets its own copy. If we create 100 student objects, we will also have 100 separate counters. Updating one of them doesn't change the others. That clearly isn't what we want, right? We also know the counter changes whenever a student is created or removed. So it has to be shared somehow, right? Now, we are looking for a place where there's only one copy of the value. Keep that idea in mind because it's the key requirement. One shared value that every object can access and update at the same time, whenever it's needed. So, why not a global variable? Technically, this could work. Every student object could update the same counter, but global variables usually make programs harder to manage. Imagine we later add teachers, courses, and classrooms. Soon we will have global counters for everything. Keep that in mind. It becomes easy to mix them up or accidentally modify the wrong one, as we have discussed in the namespace lecture earlier. The counter is related specifically to the student class. It really shouldn't live outside that class, right? According to the object-oriented design pattern. So we have ruled out two options. A normal member variable gives every object its own copy. A global variable shares the data, but it places it in the wrong scope. What we really want is something that belongs to the class itself, not to any single object. Fortunately, C++ has exactly that feature, and that's where we will look next. So here's the solution. We declare it with the keyword static. At first glance, it looks almost identical to any other member variable, but the only visible difference is that one extra keyword. A normal member variable exists once per object, but a static member variable exists only once for the entire class. No matter whether we create one student object, 100 student objects, or no student object at all, there's still only one copy of that variable. Every object refers to exactly the same piece of memory. That's why it's perfect for things like counters, shared settings, or values that should be common to every object of that same class. Now, there's one important detail about static variables that often surprises people, honestly. Let's look at how they are actually created. Unlike ordinary member variables, a static member variable isn't created when an object is constructed. In fact, it exists before the main event starts, much like a global variable, you could say. Because of that, we can't initialize it inside a constructor in a normal way. The constructor runs when objects are created. Our static variable already exists by then. Instead, we declare the variable inside the class and then we define it exactly once outside the class. So, the definition looks something like this. Notice the syntax carefully. We write the type first, then the class name, followed by the scope resolution operator, and finally the variable name. That line actually creates the storage for the variable and gives it an initial value. If you forget this definition, your program will usually compile, but the linker will complain that the static member was declared but never defined. So, now that we know what a static variable is, let's see how we actually use one. Inside the class, it feels almost like an ordinary member variable. We can read it or modify it, directly from member functions. Outside the class, we usually access it through the class name using the scope resolution operator. That's the preferred way because it makes it clear that this variable belongs to the class, not to any particular object. Technically, C++ also lets you access a static variable through an object. That works, but it can be misleading because it looks as though the variable belongs to that specific object. It's not. For that reason, you will often see static variables kept private. Then the class itself controls who can read it or modify it. Let's make all of this concrete. Let's build a small student class from scratch. Let's go ahead and do this. I'll start with the class definition. This is the first example. So at first, let's include IO stream. Then I think we will need string, so I'll just include it right away. Then class student. So we will need some private variables first. Let's declare them right away. Private, I think we could use this one as string name, and this is where our static integer student count goes. Then, okay, let's start with the constructor. String student name. Yeah, looks good. Then, yeah, then we will increase the student count like that. When a student gets created, we will increase the count of the student, and when a student gets destroyed, we will decrease the counter by 1. Then let us also declare a static function just right away. I will explain this later. So it will just return the student count for once. And now we declare the student count and int main. Here we will standard cout and initial student count, student S1 Alice, then another student S2 Bob, and then standard cout. We will check the current student count from here. Looks right. And then we will add another student, student S3 Charlie. Then we check the student count, and then we check the student count once again. So inside this curly braces, what is happening here is the student only lives within this scope. So once the scope ends, the student S3 gets destroyed as well. So what should we get here? We should get a 0 at first, then 1, 2. So we should get a 2 here, then 3, then 2 once again. Let's see. Yeah, 0, 2, 3, and 2. So that's how we use the static data members. I need to show you one thing. Here, you can see that this line within the class, it doesn't create the variable. It only tells the compiler that the class has one shared variable with its name. The actual storage appears later with this one when we declare it. So the important thing to remember from this program is every object is updating only one counter, the student count, which actually lives here. There aren't separate counters hidden inside each student. There's only one, and the whole class shares it. Now let's get back to the next slide. Static member function. Let's get back to the example once again. Just notice this one. This is the static function. A static member function belongs to the class just like a static variable does. You call it using the class name, but not a particular object. The important limitation is this. A static function doesn't have a this pointer. There is no current object, so it can't directly use ordinary member variables like name, because whose name would that even be? It can only work with static members or data passed in as parameters. So let's continue from here. I'm going to add one more function just right here. It's going to be a static one. So void, we will print the student count. Looks good. Notice that it's using student count directly. That's perfectly fine because this function is static too. Now in the main, I'll replace this one with this one. And let's do this everywhere. It looks much cleaner now. And if we take a look at the output, you will see that current student count 0, then 2, then 3, then 2, and so on. Now let me show you something that doesn't compile. Here inside the print student count, I will place name like this. The compiler will complain that a non-static member reference must be relative to a specific object. Since there's no object, there's no name. There's a name here and here and here, but those are specific to those exact objects, not the class definition, which is right here. Static member functions work with class level data, not object level data. Now let's get back to our slide. So when are these actually used? Static variables and functions become especially useful when there should only ever be one object of a class. Think about a database connection. You probably don't want every part of your program creating its own database object. That's gonna be a huge mess. Trust me. One shared connection is usually enough. So, that raises two questions. First, how do we stop people from accidentally creating multiple objects? Secondly, if there's only one object, how does everyone else find it? So those questions show up in real software all the time. The solution combines everything we have learned today. We use a static class variable to remember the one object and a static member function to give controlled access to it. Let's build a simplified version together. Let's open a new example. So, as usually, we include IOStream. Then let's build on top of the existing metaphor that we used. Let's create a database. Then let's create a static database instance. Database. Then upon creation, we'll say database instance created. After that, a get instance function. Inside the function, we will check if the instance is being created or not. We are checking if the instance is null or not. Instance equals new database. And then we return the exact instance right here. So now let's clear out something first. This pointer is shared by the whole class. It starts at null pointer, meaning no database object exists yet. Inside get instance, we check that pointer, that if it's still null pointer, we create the object. Otherwise, we simply return the already existing instance that we have. One common mistake here is forgetting to initialize the pointer outside the class like this. Just like our static counter earlier, it needs one definition. So if we compare it, it's like this one. Now, in the main function, we create two database instances like this, db1 and db2. We will just standard cout and check if these instances are same or not. Okay, let's run it. The database created should appear only once. Yeah, the database instance created. Even though we asked for the instance twice, the database created appears only once. The 1 means db1 and db2 point to exactly the same object. That's the basic idea behind the singleton pattern. So here you will see the complete picture and a summary of what we just created in VS Code. So this is what a singleton is. We combined a static variable with a static member function. The static variable remembers the one and only object, and the static member function controls access to it. Because the constructor is private, nobody outside can instantiate anything at all. The only way to get a database object is by calling getInstance. That means the class stays in control. And we can guarantee that only one instance ever exists. You will see it in many code bases, although opinions on it are mixed. Some developers like it, others don't. Those who likes it mainly because it's simple and guarantees a single shared object. Others avoid it because it creates global state, which can make large programs harder to test and maintain. For us, the important point is understanding how static variables and static member functions work together to make a design like this possible. Even though our singleton example was intentionally simple, real programs can be more complicated. Suppose one global or static object depends on another one during program startup. The language doesn't always guarantee the order in which those objects are created. So if one object tries to use another one before it exists, the program can easily crash. A common solution is called lazy initialization. Instead of creating the object when the program starts, we wait until someone actually calls getInstance for the first time. That's exactly what our example did. One trade-off is that depending on the implementation, the destructor might never be called automatically before the program exists. In many singleton implementations, that's considered acceptable because there's only one object and it lives for the lifetime of that program. So, honestly, that topic goes way beyond today's lecture, and you will study these design patterns in more detail in later object-oriented programming course or similar courses that mention software engineering or software design patterns. Thank you for listening to the lecture and have a nice day. Bye-bye.